let's study Bayesian linear regression. Bayesian linear regression is also called Bayesian regression. So let's look at a simple example where we consider only two model parameters, W0 and W1. So we are trying to do Bayesian inference. So we will place a probability distribution over these two model parameters, W0 and W1. So here is our prior density or prior distribution for W0 and W1. So now we have no data points observed yet. So if we sample this distribution, suppose we sample six pairs of W0 and W1, and then they will generate 6 lines in the data space of X and Y. Right? So W0 and W1, each pair will determine one line in the data space of X and Y. So now suppose we have one data point observed, which is this blue circle. So this will put some kind of soft constraint on the model. The likelihood for this data point is over here. So this is the values of W0 and W1 that will generate a line that is likely to pass this data point. So that is also a line, but with some variance. And you can actually compute it analytically. So this is the likelihood. Right? So this is the likelihood of this data point. And now let's look at the Bayesian inference. So we need to consider the prior distribution. We multiply the two distributions, then we will have the posterior distribution over here. So this is a posterior distribution. And if we sample the values of W0 and W1 in this posterior distribution, we have random lines over here. So we can see that they tend to stay close to these data points at this x value. And then this posterior will then become the prior for the next observed data points. So now let's say we have a second data point observed, which is over here. And then this data point has a likelihood like this. So these are the values of W0 and W1 that is likely to have this data point to be on the line. And now we want to do Bayesian inference. So we consider the current prior distribution, which is the previous posterior distribution. And now we multiply these two distributions, we have the posterior distribution after observing two data points. So this is a new posterior. And now if we repeat this process, and suppose when we have 20 data points has been observed, so this is a likelihood of the 20th data point. And after we multiply this with the current prior distribution, we will have a posterior like this. So the crossover here is a ground truth value for W0 and W1, which generate these observed points, of course with noise. So we can see this is a distribution for model parameters W0 and W1. So this is a distribution for the model parameters. So how about making probabilistic predictions for any x? That is to have a distribution of the output y for any x value. And then we will do Bayesian inference and evaluate the predictive distribution. So here is another example of predictive distribution. Here we generate data from this green curve, which is a sine wave, and plus some additive Gaussian noise. And this will generate some sinusoidal data indicated by blue circle. So this is one observed data point. Our linear regression model will make use of 9 Gaussian basis functions. So there are 9 Gaussian basis functions. And we want to predict the output distribution. So after we observe one data point, so here is our current output distribution, the predictive distribution. So this red line is a mean of this distribution, and the shade over here indicate the model uncertainty. So these are basically the variance. We can see that near the observed data point, the uncertainty is much lower than other places. And if we sample from this output distribution, we will have several instances of our model, which is a weighted combination of 9 Gaussian basis functions. And we can see all these different lines tend to stay close to this observed data point at this x value over here. Suppose we have 2 data points observed with 2 blue circles. Now we can see the uncertainty has been reduced near the 2 points. Right? So it's significantly reduced over here between the 2 observed data points. So the samples from this predictive distribution is showing over here. So they are weighted combination of 9 Gaussian distributions. So they tend to stay close for the 2 observed data points. And when we have 4 data points observed, the output distribution become further reduced in terms of uncertainty. That is a variation. So now we have 4 data points, 1, 2, 3, 4 observed. So we can see near the data points, the uncertainty is significantly reduced because now the data points cover the range from 0 to 1. So overall, the uncertainty becomes low and the confidence increases. And the sample from the predictive distribution is shown over here. We can see all the generated curves, they tend to pass the 4 points or stay close to it. And after we have observed 25 data points, now the uncertainty has been significantly reduced. So again, this red curve here is a mean of our output distribution, and the shade indicates the variance. So that is the uncertainty. And now if we sample from this output distribution, these are the models that we have sampled, so they have stayed very close to all the 25 data points and becomes very close to our ground truth, which generate the data, which is a sine wave, sine curve. So we can see that Gaussian distribution, which is also called normal distribution, is very useful and convenient. This is because for Gaussian distributions, we only need to know their mean and their variance or covariance. Then we can specify the whole distribution. And this is called mean, and variance or covariance is called the sufficient statistics. So by knowing these two statistics, we know the full distribution of the Gaussian distribution. So the mean is called the first order statistic, and variance is the second order statistic. And for Gaussian distribution, we often have closed form solution for our machine learning models. And therefore, to estimate the distribution for Gaussian distribution, we just need to obtain the mean and the variance or the covariance. So that's all we need to estimate the distribution in a Gaussian form. So this is our very brief introduction to Bayesian regression. So we can see the ingredients of Bayesian regression. So we have talked about examples with basis function-based linear regression. So that's the basic structure or architecture. And in terms of hyperparameter, our basis function may have hyperparameters, such as if it's polynomial, then that's the number of the degree, and also some prior information, such as the Gaussian distribution, the mean and variance for the prior distribution. And the parameter we are learning are typical linear regression parameters, the weights and bias. And we minimize the mean square error. And for Gaussian distributions, if we assume that we use Gaussian distributions for the model parameters and the predictive distribution, then we will have closed form solution. Otherwise, we can do stochastic gradient descent. And Bayesian methods have some nice property. One of the most attractive property is that it can provide uncertainty estimation. It can predict an output distribution with the mean and some variance or covariance. So in practice, this can be very useful because not every prediction is equal, and some predictions may be very confident and some predictions may be very uncertain. So it's good to know how confident a prediction is so that we can make decision accordingly. And Bayesian methods also make use of more information, such as prior knowledge, and they tend to lead to less overfitting compared to a comparable linear regression model. However, one of the disadvantages is that it is relatively more complex. And there's also some kind of subjectivity because the inferences are based on beliefs, and belief comes in the form of a prior distribution. So which prior to choose? And what if our prior is wrong? In this case, the model may not give a good prediction. And next, we will look at one of the Bayesian methods, variational autoencoder, which actually deals with this complexity problem. So next, we will look at variational autoencoder, VAE.